Bismillah ar-Rahman ar-Rahim. Yes, hello everyone. This is Dr. Bassam Al-Hamad. We are going to take process safety, chemical process safety, or process safety in chemical engineering industries. And as you know that you're going to have this course as online PowerPoint presentations with some explanation so that it supports you with your learning. So what I'm trying to present here today is Chapter 1. But as this is like an introduction to our course, I'm going to mention what's the textbook and what are the references that you can go back to, and what are the chapters that you're going to be covering this semester for this course, and what are the chapters that we are going to be missing out because we are limited with time and we need to select what we need to cover. Okay, so going to our next slide. So there are key acronyms. I mean, I just want to trigger the way of your thinking. So if you hear about process safety, many things could come into your mind. Something that is related to the safety of the plant and the operation of the plant, and in this case, you're talking about some kind of management of safety within the whole plant. And so you need to know an acronym as PSM, process safety management, or something could come to your head as labs. And in the labs, you're dealing with materials, and within the materials, you're dealing with material safety data sheet, which is the MSDS sheet. And that is what is mentioned here. Or you could go through many good practices, good engineering practices. They also have some kind of standards that you can follow. So you can see the words that I'm trying to reflect here, or the areas that I'm trying to reflect. I'm talking about a management or a system. I'm talking about standards as well, and I'm talking about safety, which could be in the labs, and it's more than that actually. This is just triggering where could safety could be. So it could be at the level of a person, and talking about that person who's sitting in an industry or of having columns and heat exchangers and so on. What about this guy? Is it safe for him to operate here? Well, it's good for him to have a helmet. Okay, good. To have an overcoat, so if there is some kind of fire, there's also something safety to protect him from gases. Is this area the gas concentration? The gas concentration is good enough, or he needs to wear a mask, or he needs to wear a mask on his face. This looks like a beard, look more than a mask for me. Okay, so and doesn't need to wear gloves. What about safety shoes? Maybe he needs to wear some kinds of safety shoes. Why? Because safety shoes with fingers, I didn't see that before. So maybe he needs to wear some safety shoes. Why? Because he's going to be working really hard, and maybe he hits one of the pipes that is everywhere, here and there, and he's going to break his finger, right? So talking about the safety guy, okay, I mean that person who's working within the industry, there are many things that we should take care of safety of this person, of what he's going to get inside his nose, breathing, inhaling, and what could hit him. We don't want any injury, no please. We don't want any fires, yes, no fires. Okay, let me correct that. So we don't want any fires, we don't want any explosions, okay, and so on. So the things that we need to be careful that we have things that are safe to that person. And talking about all of this as a management point of view, we are talking about process safety management, and talking about good practices and so on. Of course, we are talking about standards for good practices, and we are also going to cover that. Okay, so just to trigger our mind, we already triggered our mind with some safety concepts or terminologies, and looking at the chapters, there are more chapters actually within that book. There's also chapter 12 and 13. I didn't mention them because we are not going to take them. Sorry for that. But there are also two other chapters that we are not going to be covering. So we are not going to be covering. Relief sizing, and we are not going to be covering toxic release and dispersion models, and it's all because of the limitation of time. So what we're going to take today, we're going to take introduction for the safety and what does it mean and where it happens, and if there are some incidents that happened before and we want to consider them, and then we're going to talk about toxic materials and what is toxic. Could it be toxic to your skin? Could it be toxic to your eyes? It could be toxic by inhaling or digesting or ingestion and all that. What about industrial hygiene? How can you maintain that you're having everything built in that it should have no problem with safety? So if you're talking about the design itself, or you're talking about maybe also laws and standards that maintains everything in industries to have hygiene from any losses. And then we're going to talk about, well, if we have some gas or liquids that get released, so from where do they get released, and if they are released, how far could they go? Details of that is mentioned in chapter 5, but we are not going to capture or take chapter 5. We are going to work on fires and explosions, of course. What are the difference between fires and explosions? And then what should we do to work with those, to design and to combat fires and explosions? And then we're going to talk about the relief valves. So it's more about the pressure here. We're going to concentrate a lot about the pressure and where do we put our reliefs, and what is the difference between relief and safety valves, and what are the different kinds, the diaphragm and the spring and so on. So that is all chapter 8. But we will not do any kind of sizing. And then we want to go to the hazards, identification, and it's more towards how to identify that this is a hazard, and if it is a hazard, of course, that a certain percentage you're talking about that it becomes hazard. And what about if you have a mixture? How can you calculate this hazardness? And last, we are going to talk about the risk assessment, and talking about the risk assessment, that means how much risk do you have, and risk, it becomes risky if it happens frequently. So if it happens frequently, the likelihood, and it's very risky if it has a high impact. And these two things are going to be covered also within chapter 11. So that is our course, and today we are going to cover chapter 1, and hopefully that it will be a very successful course for you. So there are references that if you want to read more about hazards identification methods, you can go to this book by Wiley. And there's also another reference talking about the incidents that define process safety by John Etherton and Frederick Gill. So these are the other two references. But our main textbook by Crowell and Lover, I think it's the best textbook I have ever seen in chemical process safety. Okay, so chemical process safety, one of the popular scholars said that, Fawcett, he said that to know it to survive, to ignore fundamentals is to court disaster. What he wants to say here is that we should consider fundamentals to maintain that we don't have disasters. So definitions, just to get some definitions. So when we talk about safety, we just want to say that we do not want to have any loss, or we want to prevent loss. Okay, loss could be in what? It could be in certain aspects. It could be in the property. That means something happened within the building, or something happened within that instrument. It could be the property, or it could be the people. The people got hurt, which is injury, or you're talking about the people who hopefully not, died, fatality, and it could be the environment, okay, or it could be the environment. So we don't want anything to happen within these three items. So that is safety. We want to eliminate that not to happen, okay? We want to eliminate it. The hazard is anything that causes this kind of loss, a chemical or physical condition that has potential to cause damage. So the word damage here, anything cause damage and have loss is hazard. And risk, that means, okay, now this hazard which is going to cause the loss, is it high risk or low risk? Well, it is high risk. It happens every time, okay, which is again the likelihood. And if it depends on the impact, if it is a high impact or a low impact, which is the magnitude of loss and injury. So if you multiply these to each other, if it is likelihood to happen, that means it happens very frequent, like 12 times per year it happens, and when it happens it has a high impact. That is a very, very high risk. Okay, so a great guy, he said that, well, why we don't write new terms, beautiful terms for safety? It just reminds us with the details of what we are going to be talking about, or what are the concepts or the items of safety. So S for system, S for system, A for attitude, F for fundamentals, experience, E for experience, T for time, Y for you. Okay, so what is simply they want to mention here is that you cannot have safety program without a system. You cannot a system, that means a system, a management for the safety program, for entry, for the way how you put on clothing, for the instruments that you're going to use, for the electrical supplies, and what kind of wires, and where does the car should drive, and so on. So all management of the safety part. The second thing is the attitude. The second part is the attitude. That means everyone is responsible. Everyone is responsible. Everyone. And then we are going to talk about the fundamentals. And talking about the fundamentals, we should have fundamentals in the way how we deal with our safety program. So we cannot have a safety programs without fundamentals, which means when you design a column, you need to design it based on fundamentals to maintain safety. When you design a heat exchanger, you also design it based on fundamentals, and so on. And going then to the experience part, the experience, that means that things that happened before, and we need there are many fires and explosions that happened before in many different countries, and we need to make good experience from that so that it doesn't happen again. And talking about time, we need to act fast, because if we act very slowly, easily we could have some kind of damage to a property or to a person. And of course, us and you and me, we are responsible to maintain that safety. So all of us together, we maintain that safety. Okay, so if I would say what is a good safety and what is an outstanding safety program, a good safety program will eliminate any hazard. But talking about an outstanding safety program, an outstanding safety program is what? Is to have a management system. Is to have a management system to manage this safety program, to manage that safety. So the outstanding safety is definitely better than a good safety. Okay, other things that we in our introduction here is that we also should consider ethics as well. And considering ethics, there are a lot of things that we could talk about ethics. AIChE, which is the American Institute for Chemical Engineers, they have set some kind of fundamental principles. We cannot go through all of them, and we don't need actually to go through all of them. But just to mention quick stuff here, for example, being honest. being honest is really important because you need to be honest and impartial. And we had examples of some people who had a who had a problem of not following procedures, and they cause some kind of fires and explosions, and then they say, I don't know what happened. Okay, they just say, oh, I don't know what happened. And they cause more injuries, and they cause more damage to themselves and to the others. So no, you shouldn't be like that. You should be honest. And of course, you should increase your competence because things are changing always with time. Another example that also comes to my head is that you need to continue your professional development, because you will be outdated with professional standards or safety standards if you don't do that. So these are the many things that we can come to our mind when we talk about code of ethics. Okay, what accidents do happen in chemical plants? Well, accidents do happen in chemical plants. We know that. But you can see that they are somehow between these three main types of accidents. So fires, explosions, and vapor cloud explosions. So these are the types of chemical plant accidents that are very popular. And if you just look at the details of it, so fires is a type of accidents. And here we want to talk about probability of occurrence. How high is that probability? So it is high probability. An explosion is less. Toxic release is even less than them. So fires could happen more frequent than others. How about fatality? Well, fire does not have that kind of fatality, but oh my god, explosions definitely have fatality, but it will have to the surroundings to some limit. But the one that has no limits to the surroundings and it even goes further and further is the toxic release. So we can see that the occurrence is very minimal, but it has a very high fatality. And talking about economic loss, well, the most one that has the economic loss is the explosion. Sorry to say that, but if people are dead, they are not as expensive as the whole plant goes out of use and we are out of the business and the market. Okay, so this just gives you an idea about the types of accidents that we have and which one is more possible to occur, and if it could cause some kind of fatality or economic loss. I know for a moment you think that should we memorize that. Don't worry about memorization, because all our exams are going to be open book, so you're going to have everything within hand. So don't worry about memorizing, rather than you need to understand what is going on. Okay, so let's go to some kind of statistics. Talking about statistics, what is the main reason for having any statistical for having any kind of an accident or error or a problem within your system, or things that are not operating well? Mechanical is the most reasons that cause accidents here. And this is by percentage, by the way, this is 44%. And operator error is 22%. So that means if I work on the design of the mechanical part, if I work on the training for the operators, I could manage that I will have no problems at all within my system. Okay, of course there are other reasons, talking about process upsets, natural hazards, design, and so on. But what I'm trying to say that these two things that I'm trying to mention here are the main purposes that could cause high statistical errors. And talking about the number of accidents, here, the number of accidents happened due to several reasons. Again, we could go to the details. There are problems with the piping systems. There are problems with the miscellaneous storage tanks. There are problems with the storage tanks, with the Arctic piping systems, process handling. يرجع يوسف أنا أسجل يوسف وفي رياض تحت حق يبدل الماي روح لتحت وورد فوق تصرف وياه وأعطى فلوس. يلا مع السلامة. Okay, so that was just a cutout for a moment. Sorry, I'm back. So talking about the reasons here, figure 1.8, it says hardware associated with the largest losses. So which one causes the largest losses? It's always the piping systems that causes the highest losses. There are other reasons, talking about miscellaneous, whatever, unknown, causes losses. We have no hand on that, but we have hand on the piping systems that we're going to use. We have hand on the storage tanks that we're going to use, on the reactor piping systems. So if you concentrate on the most important ones, which contribute to about 80% of what we are working on, this is contributed about 80%, you can solve most of the problems that are related to the errors and of course to safety. So if I'm going to ask you about the main reasons or where you should put an eye to, of course everything is important, but definitely those ones that are the main ones that cause the largest losses. Here we are saying the largest losses, right? Okay, but it doesn't mean the others could not cause any loss, because the impact for the compressors, for example, if there's a big problem with it, we should consider that as well. Okay, what is an acceptable risk? Well, it's difficult to say because we cannot eliminate risk entirely. It just should happen, and this is life. It's a part of life. We have cars on the way. We should have an accident. It's not that we should have. It just happens that it has to happen. So what we need to talk about here is that how to deal with it and how to minimize it. Okay, so we need to know if the risk is high or not, and of course the layout of the plant and where we have exposures. We could also control how things are going, and acceptable risk should be calculated and not should be based on public perceptions, because public perceptions are always confusing. We should concentrate mainly about what we calculate as a risk. However, we should aware the public with all the possible, because they are part of what we are doing, or they're part of the whole system, so they should be aware about it. But the things that is not what they say identifies how risky or less risk as it is. Okay, so now just some kind of calculations which helps us to get the idea of the risk. So there are three methods to report accidents. The OSHA incident rate, the fatal accident rate, and the fatality rate, or the deaths per person per year. So the higher the fatality rate, that means there are more people dying per year. The fatal accident rate, that means there are more possible that accidents will happen that could cause of someone to die or to get injured. Fatality is a little different than fatal, even though that sometimes they relate to them as death or relate to them as injuries. And the OSHA incident rate is how many incidents do happen. And of course the OSHA, I did not mention the OSHA, which is the Occupation Society for Health Association. So that is an occupation safety, health. It's also related to safety and health, and it's a very popular association. Okay, so all the three methods report the number of accidents or fatalities. Okay, accidents is the incident rate, or fatalities for a fixed number of workers. So they need to fix. So why they fix the number of workers? So that they can compare from one country to another. So if I would say that I have 100 incidents per year, and someone else says I have 1,000. Okay, it could be that person who said 1,000, he's in China, and he's talking about a very big company. I'm not sure. And I just have a very small company, and that is why I have less numbers. But when I base it on a certain number of workers per 10,000 workers, and then I say that how many of the 10,000 workers per year have an incident, then we can compare, and this is why we are trying to fix the number of workers. Okay, so this is an example, and that is the OSHA stands for Occupational Safety and Health Administration, not Association, of the United States of America government, and they do consider workers are providing with a safe working environment. So their main concern is the worker. Okay, so you should put that in mind, because there's one question talking about what's the difference in OSHA and some other organization, and the differences, there are differences because here they're concentrating on workers. Okay, so the OSHA incident rate is based on cases per 100 worker years. Okay, 100 worker years. A worker year is assumed to contain 2,000 hours. Okay, how did they calculate that? 50 work weeks per year into 40 hours per week. So that's 8 hours per day into 5 days per week. So that's 40 hours per week. So if you multiply 50 into 40, that's 2,000. The OSHA incident rate is therefore based on 200,000 hours. So where did the 1,000 come other than the 2,000? So they multiplied by 100 workers. So it becomes 2,000 hours of worker exposure to a hazard. Okay, so if we have 2,000 hours of worker exposure to a hazard, how many incidents do I have in that number of hours? So I hope you got it. And this is why we are saying that on 200,000 hours, okay, again, that's 200,000 of worker exposure to hazard. So I multiply the 200,000 work exposure to hazard into the number of injuries that I have, divided by the total hours worked by all employees in that in that period covered, and that will give me the incident rate. Okay, and that will give me the incident rate that I want. And I think so we need an example, and we're going to take an example later, very soon. So just before going to the example, there are some glossary terms that if you would like to go through. First aid, we know that you need first aid if you have an injury. Incident rate is number of injuries, we just mentioned that. Lost work days, that means you're losing some work days because someone is hurt. But there is a detail here, because there are difference between lost work days and some other terms. So here are lost work days because someone is injured and he just left. Okay, number of days after, but not including the day of injury. So it does not include the day of injury during which the employee would have worked but could not. Okay, so I think it's clear. Medical treatment, you're dealing with medically through a doctor or physician or registered professional personnel. Occupational injury, that means an injury that which such as a sprain, cut, or a burn that results from a work. It happened there in that work. Instantaneous exposure, so it happens in the work environment. Occupational illness, that means there's an illness. Someone has a dizzy head because of what he had smelled, resulting from an occupation injury. So it happened through his occupation and exposure to some environmental factors. As I said, that percentage of a certain gas within the atmosphere. It caused some illness, diseases, and so on. Ingestion, he has problem with breathing. He has problem with the way of how his stomach is acting to what he had breathed. Recorder cases, that there are cases that are recorded, how many injuries, how many deaths, and so on. And fatality cases, how many people are dying. Non-fatality cases, so there are people who die but there are no lost work days. There are lost work days, recovered work days due to restricted duty, so because of the injury. And there are cases with days away from work, so because of the injury, not being able to return to work on the next regular work day. Okay, so these are all cases as well as this medical cases. They are just all terms. So I'm going back just to recall, after we have went to the details of the definitions. An incident rate is based on lost work days instead of injuries. Okay, lost work days instead of injuries and illness for this case. So number of lost work days into 200,000 work hours divided by total hours worked by all the employees. I think so. You just can read that. It's all about the definition. Okay, what about the FAR? The FAR, F-A-R, the fatality rate. Okay, talking about the fatality rate, it is used by the British chemical industry, and this fatality rate is a report the number of fatalities based on 1,000 employees working their entire lifetime. And what is the entire lifetime? That means they're assuming to work a total of 50 years. Thus, the FAR is based on 10 working hours. The resulting equation is that. Okay, the resulting equation is the number of fatalities multiplied by 10 to the power 8. 10 to the power 8. That means we are considering that they are working for 50 years, 1,000 employees, and that is the number that we multiply with. Divided by the total hours worked by all employees during the period covered. Talking about the fatality rate, okay, that is FAR, that is the fatality rate. The fatality rate is the number of deaths per person per year. So number of fatalities who died per year, or the total number of people in that population. Okay, you can read the definition if you want. And I think so we just need to work on some examples to get the meaning of it. So both the OSHA incident rate and the FAR depend on the number of exposed hours. Okay, so FAR depends on the exposed hour and even the OSHA incident rate. If you go back, the OSHA incident rate, it has the 200,000 hours, and the FAR, it multiplied by 10 to the power 8, considering the working hours that we have, and we have that 1,000 employees. And then the fatality rate, it does not depend on the exposure. Well, the number of exposed hours is poorly defined, if you can see. It just calculates how many fatalities we have per year over the total number of people. And here we just mentioned that the ones who consider the number of exposed hour is the OSHA incident rate and the FAR. So going to the example, a process has a reported FAR of 2. Okay, so it has a FAR of 2. If an employee works a standard 8-hour shift, 300 days per year, so 8 hours multiplied by 300 days per year, compute the deaths per person per year. Beautiful. Okay, it's not beautiful, sorry. So we know what you're going to do. So talking about the equation, so we have the equation. If you just look at it, FAR is equal to number of fatalities into 10 to the power 8 over total hours. So if you want to calculate the number of fatalities, we need to multiply FAR with the total hours worked. Okay, so what is the FAR? The FAR is 2. So this is 2. Multiply the total hours worked. Total hours worked is 8 hours per day into 300 days per year. And this is divided by 10 to the power 8. So we got 4.8 within 10 to the power minus 5. I know that you say, well, the number of fatalities is very low. It means that no one is dying. But if you count it, multiply by 10 to the power 5, for example, hours, and then you're going to know, well, okay, based on 10 to the power 5 hours, which is 10,000 hours, that means there's one person who's going to die every 10 to the power 5 hours. It's not one person, it's like 5 persons are going to be dying every 10 to the power 5 hours. And you just can compare now from one place to another if this is acceptable or not. And so on. I was just going to say that it's not acceptable for any person to die. But it only happens. It's like accidents. In car accidents, people die. From accidents, we just need to live with that kind of technology of what we are doing, and sometimes it causes some side effects that are out of our control. Okay, so typical accident statistics, if you look at it for various industries, it could be, we have many industries: chemicals, motor vehicles, steel, paper, coal mining, food, construction. All these are industries, and these industries here it shows in that table the incident rates that happen, cases involving the days away from work and death. So it's work and death both together, and we can see which one has a higher incident rate. And incident rate, we can see that the motor vehicles, it has a higher incident rate. Okay, a higher incident rate if I would go to 1998, which is just a more recent one. And this is much higher than the steel industries. Okay, so now from just looking at those, we know which one has a higher incident rate. Okay, so if you're going to work on any one of those industries, you can know which industry that you're going to be having an incident rate, you're going to have an incident that you're going to be hurt for some reason. What about death? Death, chemicals, it was 4, but it went really down because of all the standards that came into being. So it's much better now. But for example, coal mining, 7.3, but can you see that it was 40? And that's why there were many marches against people who work in coal mining, because many people died. It's really a very big number, very big number. And what about agriculture or construction? Sorry, construction. People died, just fall off from over the several stories. And the reason is that there were not a lot of management there for safety. Look at the number now. It's just 5. It's just 5. Agriculture went from 10 to 3.7. So you can see that things, that standard and management of standards can make things differently. What about the fatality rates, death per person per year? If you look at the death per person per year, definitely car will have an accident. But talking about the far for the number of hours, if you fix that number of hours, you will see that the motorcycle will have the highest. The motorcycle will have the highest because you're fixing the number of people. So that's why you're going to have it definitely higher and higher. Talking about bicycle is higher than car. Even though that we know that no one is going to die from a bicycle, maybe hitting a car will make him die. Okay, and you can see even airplanes. Okay, but we know that there's no data here, but it's like it could be safer sometimes to go by air rather than car. Rock climbing, there's a high. If you fix number of hours and number of people, it's very high to have this incident. The fatality rate, and so on. And again, the number of deaths that happen for motor vehicles, number of deaths that happen for work, for non-motor vehicles, motor vehicle, the one from homes, and so on. So this just gives you the details of what are the number of deaths. So acceptable risk. Talking about transportation incidents in a highway, of course, we're going to have many incidents. Okay, let me read that. The manner in which workplace fatalities occurred in 1998. So what happened in the workplace fatality? So based on the total number of fatalities, which is 6,000, this is what happened in that year. And we had the fires and explosions. These are number of people who died. These are number of people who due to harmful substances. These are number of people who died due to falling. These are number of people who died due to contact with equipment. These are number of people who died based on the violent acts, and these are number of people who died because of cars and so on, vehicles. I can't see how big is that. And actually, and you can see the highway struck by vehicle or non-highway aircraft, or within the highway is the highest. You can see the big number there. Okay, and it's just said acceptable risk. That is this acceptable? It is acceptable that it is happening, but we also can do something about it. Yeah, and for example, this homicide and suicide is very low in some countries, very high in other countries. So definitely there is something that we can work there to fix it. So talking about loss distribution, the loss distribution for onshore accidents for 5-year intervals, okay, for 5 years, over a 30-year period, there were also 7 offshore accidents in this 30-year period. So that we are talking about onshore accidents and offshore accidents in your country and other countries. Okay, it's like that. Okay, so in this 1967 to 71, we had 5 losses, and then in that period we have 9 losses, and that period has 17 losses, 16, 27, and the last one 18 losses. So we are trying to control things and have losses is less, even though that our technology is going up, the number of industries is really growing, but that is why you had high losses. but with a lot of, in 1991 and 1990, we had a lot of safety standards coming on, and everyone started obeying them by law, and this is why things have changed within this year. Okay, now talking about the crisis. We're talking about the crisis. So there are many crises that happen in our life. Japan nuclear crisis is one of them, and if you go through it, there are many things that happened. Bangladesh, for example, electrical consumption, there was a big problem that happened there. And what was the reason? There was an earthquake in Japan, and due to that earthquake, this nuclear plant that we had here, it could not manage. We could not manage to control it because of the cooling systems that we are trying to have. Sorry, this cooling system we are trying to have for these rods, control rods. Because of that earthquake, things were out of control, and the pressure got higher and higher, and then it exploded. And actually, it was also not in the required depth, and because it was not the required depth, we learned that from experience. It was very close to the ground, to the surface, and it also caused more severe problems. So the earthquake that happened, as we have mentioned, and the generators, emergency generators that worked to run the cooling system, yes, it worked, but then it shut down after an hour. And then when the cooling fails, as I have just said, the water started boiling, the steam pressure went up, and things were out of control. And then we had zirconium material with the steam. That was an explosive mix, and that was a big problem. The threat, of course, there was a big threat all over. Many people died, and a lot of things that happened. But one of the worst things that could happen was the radioactivity that was there. Seawater is very corrosive, so it also made the plant going out of function. Okay, so talking about the errors here, we had some errors regarding the design errors. So the electrical rooms were sitting at the basement, so there was no access to them, so we couldn't even control things. They were out of our hands. So that was like a design problem. Okay, and there are things about also the plant location that we could talk about, and how deep is going to be that plant. And talking about design errors, I think so I already mentioned one of them. Human nature, that they don't have everything really back in hand. So less immediate backup systems to be not well designed or maintained as the primary backups. One example is the temporary holding ponds. So there are temporary holding ponds if something goes on, but this even the temporary storage pool to which the fuel had been transferred while maintenance is performed is much smaller near the top of the reactor. So it was very small, unlike the 15-meter deep permanent storage pools. Okay, so that was one of the big reasons. The generators, it did not work for some time, so the batteries were weak and they were exhausted, so we did not have backup for that. Another example is that two plant operators, that is in Washington, D.C., Manufacturing Chemists Association, they mentioned, if you go to their website, they have some kind of case histories. So one of the case histories, they mentioned two plant operators were filling a tank with vinyl acetate, and after a few seconds, the contents of the tank exploded. Why? Of course, what happened? One operator died from fractured skull and body burns caused by a static spark. So that was a problem. Static spark jumped from the steel nozzle to the tank car. Should not happen again. What we should do, we should have something that's related to that. Okay, to the design and to act, the procedures and so on. Chemical reactivity. So we were talking about the chemist who twisted the cap of a bottle, and when he twisted the cap of the bottle of an isopropyl ether, the cap broke and then it exploded. The man died, caused by rapid decomposition. So the man died because he had some kind of bleeding inside his body, causing the hemorrhage. So we should be careful. Okay, another case for chemist association. You can see this more towards chemist, so it's all chemistry. That's why we're not talking about the design part. We talked about the design, now we're talking about the chemistry part. So the system design, ethylene oxide explosion, a process storage containing 6,500 gallons of ethylene oxide. It was accidentally contaminated with ammonia. Oh my God, contaminated with ammonia, oh my God. The tank ruptured and dispersed ethylene oxide into the air. This vapor cloud is a big problem and exploded. Oh my God. One person was killed and 9 injured. Property losses were this much, 16.5 million. So lack of design protection to prevent backup of ammonia. So there was no backup of ammonia. There should be backup of ammonia so that it doesn't get contaminated with that ethylene oxide, causing that vapor cloud of explosion. A man working in a vessel. This is like very painful because two maintenance workers, they are sitting together or they're working together. The main switch was left energized. They forgot the main switch energized. The mixer was stopped. Okay. So what did the operator do? The operator by mistake pushed one of the start-stop button. Imagine that. And the other mechanic just was killed. Okay. Bigger disasters like the one that happened in Bhopal, India, you can have a look at that within the YouTube. There are a lot of details of what happened. It was a really serious disaster that happened in 1984. And the thing that you need to specify here, the storage tank containing large amount of MIC. I didn't mention what's MIC. It is the methyl isocyanate, and cyanate is really very, very poisonous. And the amount became contaminated by water and heated by reaction. Why it was heated by reaction and why did the relief valve did not do its job? There are a lot of details there. With a backup pressure and so on. We will not go through that detail, but 25 tons toxic MIC vapor release. You see the amount that was released? How many people died? Over 2,000. Oh my God. Over 2,000 people died. This is other than people who were injured, other than the animals and the plants that were also that also died. Okay, so alternative reaction scheme or redesigning of the process with the reduced inventory. So there's something a part of the design that we should work on. So CO stripper is another thing that happens in Goreshal in 1991, and 11 people died. Why? Because the stripper column exploded and split into two halves. Why? Because the CO stripper contains the carbonate solution and ammonia and runs at a high pressure. So high pressure went out of control, it exploded and split into two halves, 11 people died. And there are some details to why did this thing happen. It was a fabrication defect, crack in the welding joint. So you imagine how welding is that important. It will not cause that defect. It is as small as you would expect that problem could be. Okay, and there was no test done before. It was just put into operations directly, and this is what happened. Other than that, power generation system just tripped. No emergency lights. Rescue time were our team were very late, and this is why time is very important factor. So this caused all the problems. How to deal with accidents? Of course, to deal with any accident, we need 1. Initiation, propagation, termination. That means what initiated this accident and what makes it propagate and what could terminate it. So if we prevent the initiation part, we are good. If we couldn't prevent the initiation part, we could prevent it from propagating and maintaining it. If we couldn't prevent it from propagating, we should know how to stop it. Stop it could also mean stopping the plant and shutting it down. Okay, so these are the 3 different defeating accident process. We have the initiation, propagation, and termination. And what examples of initiation? Examples of initiation would be grounding and bonding, inerting, putting some inert, hot work permits, human factors design. Propagation is that the materials transfer. If you're propagating or reducing the inventory or the space layout, because you know that the space layout, if everything is compact, it could cause that it could propagate very fast. If you don't have valves, the pressure build up could propagate very fast. Terminated is firefighting, dealing with it directly, open relief system, the sprinkler system, just to work on shutting off everything and dealing with it very extremely. Okay, and there is some example here, and example, for example, we had a failure of threshold of 1% drain connection on a rich oil line at a baseline of an absorber tower in a large gas producing plant allow the release of rich oil and gas at this pressure 850 psi and minus 40 degrees Fahrenheit. The resulting vapor cloud ignited from the ignition system of the engine-driven compressors. The 75 diameter absorber collapsed across the pipe rack and on two exchanger trains. Braking pipelines added more fuel to the fire. Oh my god, braking pipelines added more fuel to the fire. Fuel to the fire, imagine. Severe plane impingement on a 100,000 horsepower gas turbine, a very high horsepower driven compressor, waste heat recovery superheater train resulted in its near total destruction. What is the initiation, propagation, and termination step for this accident? Initiation, what happened? If you want to explain it, a failure of the threaded 1.5. This is what happened. What made it propagate? Release of rich oil and gas, formation of vapor cloud, ignition of vapor cloud by recompressor. So we're saying that what made it propagate. What made it terminate? Everything finished. All what had been released from oil gas, they got consumed. Consumption of the combustible materials and process. So this is what happened here. How to deal with it? We can use those technologies to how to deal with it. There are other things that we should consider with our introductory, very long lecture, is the inherent safety. The inherent safety. So inherent safety, these are the old terminologies, which is intensification, substitution, attenuation. I think they're very complicated in talking about things. So we will use easier words: minimize, substitute, moderate, and simplify. So if we can minimize our operations to better, we can substitute less toxic material, it will be better. And if you can limit the effects of some certain operation levels, so that we don't have very high pressure and so on in a certain system, and of course simplify it, and simplifying it is always better. And there are ideas here, and this inherent safety techniques again is an open book, so you always can use this available at your hand. So minimizing, change from large batch reactor to a smaller continuous reactor. So you're changing it. Reduce storage inventory. I don't want high storage inventory because it's causing me problems. So I just want to reduce that inventory. Okay, so this is the idea. Substitute. Instead of mechanical pump, I'm going to use a different pump. Instead of welded pipe, I will use flanged. Instead of using a solvent which is high toxic, I'm going to use one which is less toxic. I'm going to use mechanical rather than using mercury gauges, and so on. So you're substituting. Moderate, I'll use vacuum to reduce boiling point rather than other procedures. I will reduce the process temperature and pressures to work on less temperature and pressures rather than high ones. Refrigerated storage vessels, like for example the one for ammonia. So if you have ammonia within your process, how to store it? You want to store the gas at a certain high pressure, or you just want to make it a liquid and then store it. Liquid is much safer and is better. So you can see that we can have things differently stored or operated to have less kind of problems. If you want to talk about where did we get, dissolve hazardous material in safe solvent rather than a hazardous solvent. Operate at conditions where reactor run away. If it runs away the reactor, that means there's a problem with the reactor and the temperature is just running up or pressure is running up. It will never happen. Okay, so we need to operate at safety conditions and not only for production. Place control rooms away from operations, because if it was very close to operations where there is an explosion, control room will also explode. So no one will control, and so on. To simplify things, you can keep pipe sync systems neat and very clear to read and visualize, because if you want to act directly to the system, you need to have things that can be seen. Otherwise, you don't know what to do. For example, you don't have lights as well. That's a big problem. Design control panels that are easy to comprehend. Control panels can be very complicated. No one understands them. And when there's a problem, they do not know how to operate it. Design plans for easy and safe maintenance. So we need something that we can maintain, right? Safe maintenance. pick equipment that requires less maintenance, pick equipment with low failure rate. So we're trying to simplify things, how we can use them. We use barcodes or barricades as well. That will help us. We label the pipes, label the vessels to know what we are dealing with. Okay, so that is enough for chapter number 1, because all what we are in the hazards, we already covered those parts, and the hazards part we are going to cover later. There are some process incidents. If you would like to read, I have kept the link there at the bottom. If you can see YouTube, it's written there, YouTube. Okay, so just click it and you can go to the YouTube file and so on. If you can see, there are many cases, and these just pictures of what happened. If you want to also read more about the Buncefield in UK, what happened, and so on. So I would recommend now for you to have a look, to have a look to one of the use tools. And for my case, I would say that I have entered to the end of my session, and just have a look, and I will not say that it's going to be not painful. It will be painful to what you're going to have a look at, but please consider that this is part of what happened in life, and we should be very careful to what we are going to be dealing with in future. So all the best, and just have a look of what we have here. See you, and wish you all the best, and we are going to see you for chapter 2 soon. Good luck.
At about 2 a.m. on March 23rd, 2005, I saw
مع السلامة.